Okay, so today I'm going to walk through how the anomaly detection actually works under the hood in Netdata. So you can see I'm in the Netdata repository. So right next to in the ML folder, next to the code, there's a notebooks folder, and so we're kind of adding notebooks in here to make it easier to just see for yourself how it all works under the hood. Obviously the notebooks are, stylized representations of what's going on, all implemented in Python, but then in the Netdata agent itself, the implementation is different. It's in C++. But to understand how it all works, all the ingredients and the pre-processing is pretty much the same in here, just the implementation is different. So this notebook, you can, let me zoom in a little bit. This notebook is here for anyone. You can kind of read through it. It goes into a lot of detail, so I won't go through everything. I'll kind of just quickly go through like the main points, so you can get a feel for things. And if you're interested, then you can just click this open in Colab button. So if you wanted to play around with this yourself, you can press that button, and it will open the notebook in Google Colab, where you can just run things yourself. The only little thing, you first need to just install this Netdata Pandas library, which is what is our PyPy package to pull data from an agent into a Pandas data frame, which is just easier to work with in Python. And then from there, once that's done, you should be pretty much able to just run the whole notebook yourself and play with things. Then if you wanted to change some of the parameters, if you wanted to change the algorithm or the approach, you would be able to just play around in here interactively. But I'll just for the purpose of this video, I'll just hop back into the notebook that's already in the repository, and we'll just go through that one by one. So the main idea here is to kind of get a feel for all the what the moving parts are, what the inputs and outputs are, and so that you then, when you're using the anomaly detection in Netdata, you could kind of have more of an understanding as to situations where it might work well, metrics it might work well for, metrics it might not work so well for, or if it's behaving certain ways, you would have more of an understanding as to why it might be doing that. So we might have some examples of that as well. So the first thing this notebook, the structure is we're just going to get some raw data from one of our demo agents. We're going to actually add some anomalous data ourselves, so that we have, we're going to add some kind of random mess up the data in an obvious way, and that should make it kind of, then we know what we're looking for basically. And then we're going to kind of do the ML, and at the end then we're going to actually just dig into some visualizations and explore like what is the actual model, how does it work, how do things look, and different ways to help understand exactly what's going on. So there's lots of kind of comments and discussion in this notebook, so I won't go through it all line by line. Initially, there's a good discussion on pre-processing. So this function is a core part of machine learning is pre-processing the data to get it ready for your actual algorithm. And so when the main pre-processing that happens in the anomaly detection in Netdata is we take differences of the metrics. So instead of using the raw value at every second, we take the difference of the raw value from the current second to the last. And this helps the ML sort of focus on the changes. And it also means it's more robust than to, for some metrics, you might have metrics like uptime that are always going up or always going down, or trends in metrics. We want to be a bit more robust to trends like that. And so if you just do everything in differences, that's sort of a little trick sometimes in ML that helps you detrend in a kind of a quick way. It also means that we can apply the same approach to all metrics as opposed to having to do specific pre-processing for each. And then the other thing is we take the differences, and then we do smoothing. So the smoothing is here, and so these are, if you're familiar at all with pandas, these are typical things people do all the time, where you take a difference, and here we're doing smoothing, so we're taking a rolling average of the difference values, and that smoothing is to just be a little bit more robust to individual, like one-off differences or one-off changes. So we just do a little bit of smoothing over the most recent values, so that we sort of have more of a robust representation. And then lags, we basically, instead of just using the most recent differenced smoothed value, we take the last n. So I think by default we take the last 5. So your feature vector then becomes these kind of 6 numbers, which are differenced, smoothed, and lagged values for each metric. So it's these kind of 6 numbers that the ML is looking at, and we have some examples of that down below. So the setup here, and this kind of goes into more detail of the inputs and parameters. Pretty much the defaults in Netdata are, the most 9 times out of 10 you kind of don't need to change any of the config. So there's kind of zero configuration needed to get going with this. It basically, if ML is not already enabled on your agent, you can enable it. But in the most recent releases, it's being enabled by default now. So you should just get this out of the box when you're doing a fresh install. And these parameters kind of correspond to the pre-processing stuff we were just looking at. And by default, the ML is going to train every hour or so. It's going to train and retrain, and it's going to train on the last 4 hours of data and that's the default at the moment. But some of the next stuff we're working on the ML is to extend those 4 hours to be last 24 hours or last 3 days, or so you can have more of a history, so the ML could kind of learn more beyond just the last 4 hours. And so what we're doing here is basically I'll show you some of the parameters here. At the moment, so in this notebook, we're just going to pull some data from the London demo server and just pull it from the agent REST API. So we're going to pull CPU, which you can see there's not much going on this server at the moment. So we're going to just look at one metric and just Netdata does this for all metrics at the same time, but for this notebook, we're just going to look at system CPU, and we're going to look at the user dimension. So that's this yellow guy in here, basically. And so these are all default. These are all the parameters used. We're going to look at the last 2 hours of data, and we're going to train every hour, and we're going to train on the last hour. So this is just to do like 2 training cycles. So this is like a squashed down kind of version of what's actually really happening, where it's every hour it's training on the last 4 hours or longer if you've increased the training window. And so what it's doing here is basically just using the Netdata Pandas library that has a get data function to basically just get a data frame. And this is all you really need to see here. Is it's basically a time series, and this is the time series of that system.cpu user value. And so you can see here, this demo server, there's typically there's typically not much kind of CPU work being done on this server. So these are all pretty low values here, where you can see it's not that doing that much. And what we're going to do is we're going to just add some anomalous data to this data. So in this case, I think we're just randomly scrambling the data and multiplying it by one of these random integers, basically. So we're kind of just making some obvious anomalous data so that we can then test the algorithm itself. So how this looks here is we basically have our raw data here, and at the end then we have our anomalous data, where we've multiplied by those integers and add some more kind of random data. So you can clearly see, obviously this looks, this is a bit of a toy example here. You can clearly see where we have our normal data, and then we go into this yellow zone where we have our anomalous data. But that's the setup. The idea is we should, we're going to train on the first hour of data, retrain on the second hour, and then we're going to score. As soon as we have trained models, we'll start scoring. And so the end result, we'll be able to have an anomaly score overlaid on this chart, basically. So the ML section here kind of goes into detail as to actually what we're actually doing under the hood. So we're using the k-means for unsupervised approach. So this means that you don't have to, we don't have to have any labels. We don't have to have users flag metrics as anomalous or not anomalous or infer labels. So it's all unsupervised, the approach here. And that just means that what we're trying to do is basically measure how strange the data looks based on some normal representation of the data, which in this case normal is the the data it was trained on. So the anomaly score itself is basically trying to ask how strange does this most recent data look compared to what I've seen when I trained last. We're using scikit-learn here in this notebook, but in the agent we actually use dlib, which is a C++ library, and you can, if you're interested, you can actually just look, you can see the code right in here. You can see all the code. If you're more familiar with C and C++, you could go in there and see what's going on. Let me scroll back down. So we were here. So basically, what we do here is we initialize some models. So there's a model for each dimension, and what we're going to have is we're going to have raw anomaly scores, and then we're going to have anomaly bits, and we'll get into that a little bit more. The anomaly score is basically a distance measure. So for the latest data, what's the distance between the cluster centroids? And then the anomaly bits, we will threshold this score basically. If it passes a certain threshold, which is 0.99 by default, then the anomaly bit will become a 1. So the anomaly bits are these 1s and 0s. That's what's actually stored in the Netdata agent. We don't store the raw scores because that would have meant more overhead in the agent database. Instead, we store these 1 or 0 bits because there's actually no extra overhead of storing those bits. We were able to kind of do some bit sort of manipulation within the internal representation in the agent so that you can get these 1s or 0s for free, basically. No extra storage overhead, which is really, really useful. And so I won't go through this. This is like this loop here basically just loops over all of the data observations and does an inference and a scoring step, and then also does a training and a retraining step. So if you're curious, you can kind of see there's lots of comments in here as to exactly what's going on. But basically it's just replaying the data one observation by one observation, and building up a buffer of data, training the model, building up this pre-processed feature vector, which we'll get into more detail later, and scoring against the cluster centroids. So there's one little thing here that's probably worth calling out, is that we have it's a raw anomaly score where we take the Euclidean distance between the most recent feature vector and the trained cluster centers for that model, for that dimension. And so this raw anomaly score is just a distance measure. It's so there's one little thing we do here, which is because this distance it's just a number. It's hard. It's just a distance measure in Euclidean space. So what we do is we actually normalize the raw score to be between 0 and 1 based on the distances observed during training. So this is where we say we actually look at what was the max distance in training and the min distance in training, and then we get this normalized anomaly score, which puts it back onto a 0-1 scale, because based on what we observed in the training window. So this is what kind of means. This is the trick that people do a lot of the time to make sure that you have an anomaly score that's a nice kind of 0 to 100 type metric. And so you can have something closer to 1 is more anomalous. Something closer to 0 is less anomalous. That's the idea there. And then the anomaly bit itself is basically if this is where we set the 0 or 1. It's actually set to 100 in the agent because it sort of behaves then like a percentage when you aggregate it. But the main idea is that if the anomaly score is above a threshold, then we flag the anomaly bit gets turned on. And this threshold at the moment is 0.99, which means that if for an anomaly bit to be turned on, the X feature vector of the most recent data that you have, so the most recent of these 6 smoothed, differenced, and lagged values for system.cpu.user, if that's as far as if that's as far as the furthest 1% we observed during training, that's where the 0.99 in this dimension, in this threshold comes, then we're going to say it's anomalous. So basically what we're saying is the definition of what's anomalous is basically anything that's as distant or more distant than the strangest 1% we saw during training. And so if you can, these are configs, you can in the ML code, in the configuration for the ML, you could change this. You could have this, at the moment it's set to, let me just show, it's easier to show when I look at these. At the moment it's set to 0.99, but if you found that was too noisy for you, you could easily just, and it's all explained here in the docs, but I'll go down to the configuration section. So it's this one here. At the moment it's default to 9.99, but if you found that it was too noisy, you could change this to 1.5 or 2, something like that, which would be, or if you wanted more, you could put it down to 0.90, which, so that's just saying that, well, what I want to flag as anomalous are things that are as anomalous as the most, as anomalous or more anomalous to the most 1%. So it's like it's 1 minus 99, or if you change this accordingly, so you can increase this number to sort of be stricter, or you can decrease it to be a little bit more looser to get more anomalies. But generally, this is a typical enough. This is a pretty typical standard parameter that's used in a lot of anomaly detection libraries and use cases. So this is kind of what's going on here in terms of the scoring. The training is kind of similar. It's pre-processing to get a instead of one feature vector, it's going to pre-process the whole last 4 hours to get a big matrix of feature vectors. But the idea then is it's going to fit, and what we're really interested in is the cluster centers. So the cluster centers are the representation. The cluster centers are the model basically, so that they're what we're comparing against. That's what we're learning. So that's what the ML is trying to learn. It's trying to say, okay, we have 2 cluster centers for each model. So it's trying to say, I'm allowed to have 2 cluster centers. What's the best possible set of numbers I could make to represent the training data as best I can, given I can only use 2 clusters and each cluster has 6 numbers. And we'll actually look at the cluster centers down below, where we kind of drill into this in a bit more detail. So I'll actually pick it up a bit. I think I'm going a bit slow. Basically, the end result of all this is you have your raw metric, which is in this case was system CPU user, and then we have the anomaly score, which is the actual raw anomaly, the raw normalized anomaly score. So you can think of this as 19%, 33%, and then we have the anomaly bit, which is a 1 or a 0 based on if this is greater than 0.99. So in this for this particular example, they're all zeros, but there's in our anomalous data at the end, there would be some anomaly bits probably, and which we'll see that now. So next section kind of just visualizes all this. So at this point we started with our data frame where we just had the raw metric. Now we have the score and the anomaly bit, and so the next section just kind of plots them all on top of each other. So you can see here we have our raw data, which is the top chart, and then we have the anomaly score, which is the second chart. And you can see we're missing an anomaly score for the first half because we had to wait until we had enough data to actually train on, basically. So it was only after about an hour's worth of data came in that we had a model trained that we could then start scoring. And you can see here that, okay, the anomaly score, it kind of randomly bounces around sort of low numbers, low percentage numbers between 0 and 1. Sometimes it'll randomly jump up to 1 or around that. Typically a rule of thumb is about 1% of the time you will get sort of an anomaly, but then within the yellow window you can see it gets really elevated and it stays elevated, and correspondingly then if we threshold this and look at our anomaly bits, we can see the anomaly bit was always 0, and then in the anomalous window it was on most of the time. Once or twice it turned back off kind of randomly, and you can see typically sometimes this particular spike here it looks like it went close to 1, but it must have just went not close enough. Sometimes you do get anomaly bits in the normal data. That's just normal, and that's kind of just based on the fact that we're using that 1% rule. So like 1% of the time randomly you're probably going to get some anomaly bits just turned on or off, But the main idea is that they're all going to happen randomly across all your metrics at some time. It's when they all kind of come on at the same time, that's when the anomaly rate on your node is going to get elevated. So that's what the main kind of anomaly advisor in Netdata is trying to take advantage of. So then the end result is this last plot here, where we now have our raw data. We have this kind of orange anomaly score, and then this green anomaly bit. That's what's actually stored in Netdata in the agent. So in the Netdata agent now, along with every single metric, you also have this 1 or 0, which is this anomaly bit, for free with no extra storage. So how this actually works, this goes into much more detail around like featurizing and pre-processing. But basically, what our representation, at this particular timestamp, 445, instead of using the most recent smoothed and lagged and differenced value of system CPU user, we're going to just use these 6 numbers basically, which is the most recent one and the 5 lagged versions of it's 5 lags previously. So obviously this is 445. These are random samples here, so they're not in order. But this is 445. So this value here would have been the same one from 444, shifted. So basically what we're saying is, at this particular timestamp, these 6 numbers are a representation of the most recent data for this metric. And then the question becomes, how anomalous is that based on the trained cluster centroids, which are also 6 numbers like this. And so here's the centroids here in this particular case, where we can see they're kind of similar in this case. There's not much interpretation between them. You could imagine if you had a metric that had sort of 2 types of behaviors, then maybe maybe it was like a on off, and then maybe it was a sort of a period of time where it was kind of the inverse of that. But then you could kind of think of these centroids as they would capture both those 2 types of behaviors. But often in our metrics we have multiple behaviors, and we can't really know in advance. So the main thing is that as long as these 2 centroids do a decent enough job of at some sort of separation and some sort of encoding of what's normal within your data, then any sort of changes will jump out across either or both of these centroids. Basically, that's the main idea here. And so to get an anomaly score, so if I wanted to get an anomaly score at this particular timestamp, I'm literally just doing a distance measure of this vector here against each of these 2 vectors here, and that's the raw anomaly score we were looking at above. And so there's a few different ways. The last few bits to go through is there's a few different ways we visualize this down below, just to try and make it clear. The first one is like a heat map, where we take there's 22 rows on this heat map. The first 10 rows are randomly sampled normal data from that first part of the time series, and the second 10 rows are sampled from our yellow period that was anomalous, and the last 2 rows are centroids themselves. So you can see, if you kind of just look at this heat map and squint, you can kind of see that this middle 10 or this second 10 here, you can see the numbers are much different than the normal data in the first 10 and what the centroids themselves are. So obviously this is kind of just a way to visually see, like, there's clearly a difference when you look at this heat map between the anomalous data and the randomly sampled normal data. And that's the main point that a lot of the charts down below are trying to get. You can look at this as a time series. So if we actually make a line for each feature vector, the dotted lines here are the anomalous observations, and the solid lines are the normal ones. And just looking at this here, you can kind of see the solid lines are the normal ones. They all kind of cluster down together next to each other, whereas the dotted lines they're clearly different. They're kind of there's a lot more noise in them, and there's a lot more variance in them. And so this is just another way to try and do that. You can look at this as a bar plot. So if we look at the bar plots separately for each observation, you can see, like, these ones they're all low value numbers, and so you can imagine that these are kind of all similar. And then it's when you get into the anomalous ones, you can see, okay, they're much bigger numbers, and in reality you could have big numbers, negative numbers. any sort of difference basically is going to be picked up by that distance measure. And so that's like one way of another way of visualizing these, to try and think about what's going on under the hood here. And then the last, I think there's one more way, and then you can see the centroids themselves are obviously similar to the top two. They're more different to the anomalous ones. And the last way to kind of look at this as well, sometimes that people do, is to look at scatter plots. So another way to think about this is we're in our sort of our 6-dimensional space, because we have these 6 numbers. And so if you just take every pair and do a scatter plot, and here we're coloring by the blue dots are the normal data, these 2 green dots are the centroids, and then these kind of orangey yellow guys are the anomalous data. And so if you color them like that, and then just plot every scatter plot, every pair of scatter plots, you can kind of see it's pretty clear that the blue stuff kind of always hangs around these 2 green guys, and the anomalous observations tend to be spread out much more and much more distant. So this is like the one last way to visualize this in terms of space. It's some sort of the reality is we're in a 6-dimensional space here with these feature vectors, but you can kind of look at it 2 at a time, and you can kind of get a feel for this is how it's working in terms of distances. So yeah, that's a quick walkthrough of this notebook. This is mainly kind of how these are the main ingredients and the ML formulation for the anomaly detection that we've done. As of V1, we're working on more stuff to do things like extend the training window, to use multiple models for inference, lots of different improvements that are ongoing. But this is the main idea here is this kind of unsupervised clustering based approach based on the pre-processing. That's the main idea. And once you kind of have that, you can understand. It becomes easier to kind of think about and reason about why you might see some elevated anomaly rates sometimes, and why you mightn't see them other times. So yeah, thanks for watching. And if you've any questions, just feel free to hop into our Discord, our community, or make a GitHub discussion, or just email us. All emails and contact details are in the notebook. Thank you.